Chapter 1, Section 3, Evaluating Limits Analytically. All right, now it's important to remember that the limit of a function, f of x, as x approaches c, does not depend on the value of the function when x is equal to c. It might not even be defined at it. However, in many of the elementary functions where it is defined, the limit turns out to be exactly whatever you would get if you just plug c in, f of c, which is what we refer to usually as direct substitution. So it says, in these cases, the limits can be evaluated by direct substitution, which means the limit as x approaches c of f of x equals f of c. Now, these kinds of functions are what we call well-behaved functions. There's no aberrations. There's no holes. There's no vertical asymptotes. There's no breaks in the graph. What we refer to is that we say it's continuous, that there's no breaks when x is equal to c. Now, the following properties and theorems that I'm going to present to you were all proven by mathematicians that lived many years before us using the formal epsilon delta definition, or from using properties that they proved so that they can use them in the next property that they were trying to prove, and so on down the line, and theorems the same way. So as Newton, who again is one of the guys that is probably more, maybe even more than Leibniz, Newton was quoted as saying to one of his rivals back in the 1600s, Robert Hooke, had said, "What Descartes did was a good step. You have added much several ways, and especially in taking the colors of thin plates into philosophical consideration. If I had seen a little further, it is by standing on the shoulders of giants." What he meant from that was he took what Descartes had and he built off of it. He is standing on the shoulder of giants. He is standing on the work of earlier mathematician Descartes. So what we're going to do is we're going to stand on Newton's shoulders and some of the other mathematicians, and we're going to be able to come up with properties and different theorems and such that are going to help us to analytically evaluate limits, but without having to go through the muss and fuss of an epsilon delta proof. So we're going to start off with some of the most basic of the properties. In fact, it's even entitled in your book, Basic Function Properties. It says, let b and c be real numbers and let n be a positive integer. The limit as x goes to c of b is equal to b. Well, that makes sense. If b is a constant, if it's a real number, it's not changing. It's a constant function, horizontal line. So the limit as x approaches c of b is going to be equal to b. And then this one, the limit as x approaches c of x, well, if x is approaching c and we're taking the limit of x, then it is approaching c, that it's equal to c. It's as if we have directly substituted the c in to the expression that we're taking the limit of. Same thing here. Only this one has to do with a positive integer exponent. The limit as x approaches c of x to the n is equal to c to the n. Again, it looks like we've done direct substitution. We just plugged the c in for that. Now, we can't always do that, but as I mentioned before, if they are well-behaved continuous functions at c, then we can get away with it. So using property number 1, the limit as x approaches 5 of 9 is 9. Using property 2, the limit as x approaches 5 of x is 5. Using property number 3, the limit as x approaches 5 of x squared is 5 squared, or 25. No proof is needed. We can make that statement. Now, if for some reason we were in a class and they asked for the proof of it, we would either have to base it on these properties if we've been given these properties already, which we have, or we would have to go back to the definition. Speaking of some more properties here, in this particular theorem, properties of limits, if b and c are real numbers and n is a positive integer, and we let f and g be functions with the following limits. So these limits are already established. The limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is K. Then we have these 5 properties that said, for example, scalar multiplication means we're multiplying by a constant's b there. The limit as x approaches c of b times f of x, b times that is just equal to b times L. So whatever the limit of this is, we just multiply it by b. The limit as x approaches c of the sum or the difference of f of x and g of x is the sum or the difference of their limits. The limit of the sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit for a product as x approaches c of f of x times g of x, well, this is equal to this limit times this limit. So the limit of a product is equal to the product of the limits, L times k. The limit as x approaches c of f of x divided by g of x, assuming that g of x is not that k is not equal to 0 here. Well, I'll make the statement that k cannot be 0, is equal to the quotient of their limits, L divided by k. And for a power, which is just an expansion on a product, the limit as x approaches c of f of x raised to the nth power. Well, we know the limit of f of x as x approaches c is L. This is equal to L raised to the nth power. So these properties above and these properties that we've already looked at and these properties here allow us to be able to start looking at limits of polynomials and rational functions, and we're getting our way to some of the other elementary functions little by little. So let's try an example here. All right, we have the limit as x approaches 3 of 3x to the third plus 5. Now, I'm going to write it out the long way. I'm going to write this, and hopefully you can see this okay, is the limit as x approaches 3 of 3x to the third plus the limit as x approaches 3 of 5. Now, the reason I can get away with this is because of the sum difference property that we just looked at 2 minutes ago. Now I'm going to use this scalar here. I'm taking the limit as x approaches 3 of 3x to the third. Well, if that 3 wasn't there, I would just be using the third of the basic properties that we originally started with. I would just plug 3 right in for that. But now the scalar is times that. So this is going to be 3 times 3 to the third. And of course, the limit of a constant is just that constant. So this is going to be plus 5. So this is 27 times 3 is 81, plus 5 is, my limit is 86. All right. Now the next one's a little tricky, and I wouldn't expect you to get it right away, but I'm going to kind of show it to you. So I'm going to write this as the limit as x goes to 0 of the tangent of x times 1 over x. I think you'll agree with that. I just did a little bit of algebra. Then I'm going to write this as the limit as x approaches 0. Now the tangent of x is the sine of x over the cosine of x times 1 over x. I'm going to write this as the limit as x approaches 0 of, I'm going to write this as the sine of x times 1 over the cosine of x times 1 over x. Now I'm going to take this and multiply it together. I get the limit as x approaches 0 of the sine of x over x times 1 over the cosine of x. Well, as it turns out, I have a product. So this is equal to the limit of x minus, as x approaches 0, of the sine of x over x times the limit as x approaches 0 of 1 over the cosine of x. Now, this guy we had in the previous section. We found this by using a table of values. We found it numerically, and then I went ahead and graphed it for you. And this turns out to equal 1. Well, in this case, because cosine of x is defined at 0, and because it's continuous at 0, there's no hole in the graph, no vertical asymptote of the cosine graph at x equals 0, then this is well behaved at x equals 0, and I can say that this is 1 over the cosine of 0, which is 1 over 1. So all this equals 1. That was a little trickier. All right. But you can see how we can use the properties to our advantage to evaluate limits and not have to prove them with a definition, but to know that these are indeed the limits of these functions. All right, so next up we have a bunch of theorems, and then we'll do some examples, but we have a bunch of theorems for different kinds of functions. Theorem here at number 4 says the limit of polynomial and rational functions. There we go, got to put an S on the end. If P is a polynomial function and C is an element of the real numbers, then the limit as x approaches C of P of x is equal to P of C. Direct substitution. If r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c doesn't equal 0, then the limit as x approaches c of r of x, this fraction, this rational expression, is equal to r of c, direct substitution, as long as we don't get 0 in the denominator. Just can't have 0 in the denominator. So based on that, if I said, let's evaluate this limit, well, I have a rational. It's not going to give me 0 at 2 if I plug 2 in for x. So I'm going to use direct substitution. This is this theorem right here. Again, standing on the shoulders of those giants to do all the grunt work for us. And I have 2 squared minus 2 minus 3. Hopefully you can see that. All over 2 plus 3. So this is 4 minus 2 minus 3 all over 5. I get negative 1/5. Now I would have hated to have created a table of values and plug them into here to do that work even with a calculator, and the graph probably wouldn't have been too much of a help, although eventually if I zoomed in enough I would get it and use the trace. But with here it's just direct substitution. Those are the best kind of limits. Another type of function that you can use direct substitution under the right circumstances are radical functions. The limit of a function involving a radical. Let f be a positive integer. The following limit is valid for all c if n is odd, because you can take, an odd root of positive or negative number, and it's valid for c greater than or equal to 0 if n is even, because you can't take an even root like a square root or a fourth root of a negative number. And it says that the limit as x approaches c of the nth root of x is the nth root of c. Again, direct substitution. Really nice. So I'll do an example like that here in just a second, but I'm going to combine it with this theorem. The limit of a composite function. If f and g are functions such that the limit as x approaches c of f of x is L, and the limit as x approaches L of my outer function f of x is f of L, then the limit as x approaches c of f of g of x is f of the limit as x approaches c of g of x, which is f of L, whatever that might turn out to be. So in this case, I have a polynomial function, that's my g of x. I have the square root, that's my f of x. It's saying if I plug 0 into a polynomial, I get the limit. This would be 9, so this is equal to the square root of 9, which is equal to 3. See how simple this turns out to be. Very difficult epsilon delta proof. Now let's throw in the trig functions. If c is a real number and it's in the domain of the given trig functions, then the limit, I have 6 of them here because of the 6 trig functions, as x approaches c of the sine of x is the sine of c. The limit as x approaches c of the cosine of x is the cosine of c. And on down the line, all the way down here, the limit as x approaches c of the cosecant of x equal to the cosecant of c. So as long as I don't get 0 in the denominator, I'm good. And this is allowing, again, direct substitution each time. Really nice. Don't have to go through a table or a graph or an epsilon delta proof. I'm emphasizing that a lot because it's a real time saver. All right, if we consider these next two limits here, the limit as x approaches pi over 2 of x times the sine of x, this should be equal to, using my properties, the limit as x approaches pi over 2 of x times the limit as x approaches pi over 2 of the sine of x. Well, this is going to be just pi over 2 times, and this is going to be the sine of pi over 2, which is 1. So my limit is pi over 2. And in this case, this is the limit as x approaches 0 of the cosine of x squared. Well, this is a composite function, so this is the same as the limit as if I plug in 0 of the cosine of 0 squared. Well, the cosine of 0 is 1. 1 squared is 1. Nice. Now, all the limit properties that we've just discussed, as I've tried to emphasize, involve direct substitution. But what happens when we use direct substitution and we get 0 in the denominator? Well, in this case, the limit as x approaches 1 of x minus 1 over x squared minus 1. If I plug in, I get 1 minus 1 over 1 squared minus 1. I get 0 over 0. Do you remember what I called this before in the previous video? I called this an indeterminate form. Now, indeterminate does not mean undefined. As it turns out, this limit actually exists. It's just that you can't tell it by looking at this. But remember, we did this on one other problem. I did a little bit of algebra. And if I rewrite this by factoring the denominator and canceling top and bottom the factors of x minus 1, I have the limit as x approaches 1 of 1 over x plus 1, where I can use direct substitution. Well, wait a minute. Do we know that this limit is the same as this limit? It seems like we should have a theorem about this, because these two functions are exactly the same, except at positive 1. Because at positive 1, this is indeterminate. At positive 1, this is actually a number. So we need to look at a theorem in which we are analyzing functions that agree at all but one point. And like back here, that point was 1. Let c be a real number, and let f of x equal g of x for all x not equal to c, in an open interval containing c. Then the limit of g of x as x approaches c, that's supposed to be approaches c, exists. And then the limit of f of x also must exist, and the limit as x approaches c of f of x has to be the same as the limit as x approaches c of g of x. If they agree at all but one point, then the limit exists of one of them, then it's going to exist for the other one. So I'm telling you that this is equal to the limit, it's the same guy up here, as x approaches 1, 1 over x plus 1, which is 1 over 1 plus 1, or 1/2. So the limit of, and you say, no, you're going to get 0 over 0 with direct substitution, not by using this theorem. And this guy comes in handier than you might expect. Now, when you're doing limits, you need to have some kind of a game plan or a strategy. You want to be able to figure out which limits you can just plug in and use direct substitution. You also want to know that if it can't be evaluated by using direct substitution, then maybe you could do what we did here and find a function that's similar to it, that agrees at all values except for that value x equals c, and then we use this theorem. Or if worse comes to worse, we use a graph or a table to make sure that we get our answer right. Now, let's evaluate the limit as x approaches 5 of x squared minus 4x minus 5 over x minus 5. Direct substitution is going to give me 0 over 0, indeterminate form, so I'm going to do the trick that I did up here. As it turns out, this guy factors oh so nicely. This is x minus 5 times x plus 1 all over x minus 5. And this is going to give me the limit as x goes to 5 of x plus 1. And I can use direct substitution here. The limit exists, and it's equal to 6. So that means the limit of this is equal to 6. Kind of cool. Now, let's give you one that's a little trickier where factoring doesn't bail us out. But we can still use a little bit of algebra here. The limit as x approaches 0 of the square root of x plus 4 minus 2 all over x. If I use direct substitution, I get the square root of 4, which is 2, minus 2 is 0 on top, 0 on the bottom. Can't use that. Doesn't factor. So I'm going to do a little trick involving the conjugate of the numerator. Now that's an expression maybe you may have forgotten, but the conjugate involving an expression with a radical, it's essentially changing the sign in between the two terms. The conjugate of a minus b is a plus b. The conjugate of a plus b is a minus b. Well, the conjugate of the square root of x plus 4 minus 2 is the square root of x plus 4 plus 2. And I'm going to multiply top and bottom by that. Now you say, well, what happens if this is equal to 0? Well, as x goes to 0, you can see that this is not going to be 0. In fact, this is going to be a positive number. So I can multiply top and bottom by the same positive number. This would give me the limit as x goes to 0. Up top, I do a little FOIL action. The outer and the inner kind of cancel one another out. So I get the product of the first terms, which is x plus 4, minus the product of the last terms, which is 4. And that's all over this x times all of this. Hopefully you can see that okay. These are going to cancel. I get the limit as x goes to 0 of x all over x times the quantity of the square root of x plus 4 plus 2 and the quantity. You can see why I've gone through these steps, because this is what's given me 0 over 0 with direct substitution. I have a factor of x top and bottom. Well, these factors cancel, just like the, what was it, the x plus 5s or the x minus 5s did, or the problem before that. And I think they were x minus 5s in the problem before that. These x's cancel. I get the limit as x goes to 0 of 1 all over the square root of x plus 4, all that plus 2. Well, in the denominator plus 2. So now if I use direct substitution, I get the square root of 0 plus 4, which is the square root of 4, which is 2. I end up with 1 over 2 plus 2. And when's the last time somebody asked you what 2 plus 2 was? It's still 4, and I get 1/4 as my limit. Now there is one other approach that they mention, and not very often. I can't remember the last time it was used on an AP. But there's another approach to finding the value of a limit, and it's called the Squeeze Theorem, or sometimes it's called the Sandwich Theorem, although I'm used to calling it the Squeeze Theorem. The Squeeze Theorem says, hey, find two functions, one that's always less than or equal to the function in question, one that's always greater than or equal to the function in question, for all x in an open interval containing c, except possibly it's c itself. If the limits as x goes to c of the n functions here, the one that's always smaller, the one that's always bigger, is equal to the same number, then this guy here in the middle is forced to have a limit exist and would be equal to L. If I have a 90-pound individual here at f of x, and I have 200-pound individual to the left, a 200-pound individual to the right, if they grab a hold of each of an arm and they go in the same direction, so does f of x. If this guy goes to L and this guy goes to L, then this guy in the middle's got to go to L. Okay? Notice I'm saying go to L with no H, no E, and only one L. All right, so now these two very special trig limits, this guy we've already had before, we figured him out using a table back in section, I think it was section 2 here. The limit as x approaches 0 of the sine of x over x is equal to 1. The limit as x approaches 0 of 1 minus the cosine of x over x is 0. Direct substitution gives us indeterminate form, 0 over 0. But the Squeeze Theorem, and I believe these are both shown in the textbook. I'm not really going to bother showing you the functions k and or h and g here, but these are both proven by using the Squeeze Theorem. So now I will show you a couple of examples, and this could show up quite easily on a AP test question. And it says, what's the limit as x approaches 0 of the sine of 2x over x? Now this is pretty close to this guy, except there's a 2 there. So what I'm going to do is I'm going to do a little finagling. I'm going to multiply top and bottom by 2. Now, the reason I did that is because the expression 2x here and the expression x here need to be the same expression. So now I have a 2x here, I have a 2x here, I also have a 2 out in front. But I am allowed, when I am multiplying by a constant, to have that scalar out in front. So I'm going to think of this as 2 times the limit as x goes to 0. Hopefully you can still see this okay. Of the sine of 2x over 2x. Now, as x goes to 0, would you agree 2x is going to go to 0? And if I let u equal 2x, then what I have gotten here is I have 2 times the limit as u goes to 0 of the sine of u over u. And all this is equal to 1. So I have 2 times 1, which is 2. All right, kind of sneaky. This one's a little bit simpler because the x of the sine expression is 1x. But my denominator is 5x. However, if I wanted to, I could do a little finagling and think of this as 1/5 times the sine of x over x, which is 1/5 using the scalar property where I can bring that out in front. The limit as x goes to 0 of the sine of x over x. Well, all this is just 1 from this property right here, this theorem. So I have 1/5 times 1, or 1/5. So lots of practice needed to feel confident and have a good enough knowledge of the different kinds of problems that you might encounter, not only in an assignment, but also on the AP. So practice, practice, practice.